As the Earth formed, it was rotating on an axis perpendicular to the solar plane, just like all the other rocky planets. Today, it's off by 23.5 degrees. The 1970s Apollo missions to the Moon collected 400 kilograms of moon rocks. That's 900 pounds on Earth. These rocks showed a remarkable similarity to rocks here on Earth. This indicates that they were made at the same place. An analysis of the oldest moon rocks showed that they are the same age as the oldest rocks found on Earth. This indicates that they formed at the same time. These, along with many other Earth-Moon system characteristics, supports the idea that the Earth-Moon combination was the result of a massive collision called a giant impact hypothesis. Here's an animation created by Fulldome that illustrates how this may have looked. It's a hypothesis instead of a theory because there are a number of variations and not enough data available to enable definitive selection of the right combination of possibilities. The hypothesis that currently comes closest to what happened has it that a planet the size of Mars, called Theia, moved in from the outer solar system with major quantities of water and collided with the Earth shortly after it had formed. It hit at a 45-degree angle, traveling at around 4 kilometers per second. That's 2.5 miles per second. The collision would have tilted the Earth, liquefied, vaporized, and homogenized the mantles of the two planets and ejected massive amounts of matter into space where it coalesced into the Moon. The key reason for this scenario is the similarity between rocks from Earth and the Moon. We'll focus on oxygen. Among all chemical elements, oxygen has a combination of properties that make it uniquely important in solar system development studies. It's a principal constituent in most minerals, rocks, and water. In addition, it's light enough, with 8 protons, to have 3 stable isotopes, one with 8 neutrons, oxygen 16, one with 9 neutrons, oxygen 17, and one with 10 neutrons, oxygen 18. With modern mass spectrometers, we can accurately count atoms with different masses even if the difference is only 1 neutron. We'll cover mass spectrometers a bit later in this chapter. You'll recall that the elements contained in the molecular cloud fragment that formed the Sun and the Solar System were distributed throughout the cloud. But the ratios of various elements will vary at different distances from the center as the solar wind impacts lighter materials more than heavier ones. Because oxygen combines to make gases like carbon monoxide and H2O water vapor, and also combines to make solids like iron oxides and silicates, it would have separated into various reservoirs early in the solar system development, with varying percentages of each isotope. This makes it a natural tracer for identifying different reservoirs and the objects they eventually formed. Here on Earth, we find that 99.76% of the oxygen is oxygen 16. Only 0.4% is oxygen 17, and 0.2% is oxygen 18. But physical processes can change these ratios for any particular sample. One of the best examples of this is water evaporation. The lighter isotope, oxygen 16, tends to evaporate faster than oxygen 18. This makes the ratio of 18/16 larger in a water sample and smaller in an air sample. The same process will play out for oxygen 17 proportionally by mass. The process is called isotopic fractionation. To take deviations like this into account, scientists measure the variations in the ratios of 17/16 and 18/16 against a standard called the Vienna Standard Mean Ocean Water. Here's a graph that maps the 17/18 ratios for various substances: limestones, basalts, quartz, air, and ice. Note that all the data points fall on a line. It's called a terrestrial fractionation line. All oxygen on Earth fits on this line. Additionally, the fact that Earth's water fractionation is on the same line as the Earth's rock fractionation indicates that the water and rocks formed in the same place. The lines are quite different for meteorites. The Allende meteorite that struck Mexico is a good example. A number of minerals were examined. None of the oxygen isotope ratios fell on the terrestrial fractionation line. The Allende line is different because the oxygen isotope percentages in the volume of the circumstellar disk where the meteor formed were different. A team of scientists from Switzerland and the US analyzed over 30 moon rock samples across 15 rock types from Apollo 11, 12, 15, 16, and 17. Every single one fit on the terrestrial fractionation line. Here we have shown just 3 of them. This indicates that the rocks on the moon and the rocks on the Earth formed in the same place. This in turn supports the idea that the Theia collision hit with sufficient force to homogenize the 2 planets' mantles. This also supports the idea that Theia brought us our water. We have already determined that the Earth's water and rocks formed in the same place. And given that the Earth originally formed without water, Theia must have formed in the outer solar system with lots of water. When it collided, its water became a part of the homogenized mantles for the Earth and the Moon. The reason all this is important for our how old is the Earth purposes is that the homogenized mantle would have been completely magma. Thus, the rocks that formed from this magma will be the oldest rocks on Earth, and the same would hold true for the Moon. Determining the age of rocks is called geochronology. But before the early 20th century, there was no way to do it. In the 1920s, a British geologist named Arthur Holmes, the father of modern geochronology, came up with an accurate method called radiometric dating. The method requires that the rock contain at least some measurable amount of radioactive materials such as uranium and the lead it decays into. To understand how we can use the uranium to date rock, we'll go one level deeper into just how this dating method works. We'll cover how we know what uranium radiates, how we know how long it takes uranium to decay, and how we measure how much uranium has decayed into lead in a rock sample. We'll start with radiation itself. At the turn of the 20th century, radioactivity was discovered by the French scientist Henri Becquerel. Using uranium salts, he was able to blacken a photographic plate. Here's a photograph of the plate. Further research by Becquerel, Ernest Rutherford, Madame Curie, and others discovered 3 types of radiation. Here's how they did it. A radiation source shines on a lead plate with a small hole in it to create a beam. The beam is directed at a fluorescent screen. The screen flashes when it is struck. Without any electric field present, the beam illuminates a single point on the screen. But when an electric field is applied, the beam is separated into 3 components. One is deflected upward by the electric field, indicating that it consists of negatively charged particles. These were named beta rays. One is deflected downward, but not as far as the beta rays were deflected upward, indicating that it consists of positively charged particles that are more massive than the beta rays. These were named alpha rays. The radiation that continued to hit the center was not affected by the electric field and therefore has no charge. These emissions were named gamma rays. Radiation research has been going on in nuclear labs around the world ever since those days. What we know now is that alpha radiation comes from an unstable nucleus that disintegrates into a lighter nucleus and ejects an alpha particle, which is always 2 protons and 2 neutrons. That's a helium nucleus. This is called alpha decay, and it decreases the radiating atom's atomic mass number by 4, and it decreases the atom's atomic number by 2, changing its nature from one element to another. We see that alpha decay changes uranium-235 into thorium-231 and uranium-238 into thorium-234. Beta radiation comes from an unstable nucleus that ejects a neutrino and an electron, turning one neutron into a proton, and upping the atomic number by 1 while leaving the atomic mass number unchanged. This is called beta decay. Here we see that beta decay changes thorium-231 into protactinium-231 and thorium-234 into protactinium-234. Gamma rays are extremely energetic photons and constitute the most dangerous form of radiation. They are produced when an excited nucleus returns to its ground state, much like when an excited electron around a nucleus produces a photon when it drops to its ground state. Only gamma ray photons have 1,000,000 times more energy. Here's a measured sample of uranium-235. The rate at which unstable radioactive nuclei decay in a sample is called the activity of the sample. The greater the activity, the more nuclear decays per second. This is rather easily measured with devices like a Geiger counter. Here's a 5-second run illustration. Our uranium-235 sample is decaying almost 19 million nuclei per second. Given the number of radiating molecules in a sample and measuring the activity, we can calculate the probability for any one molecule to decay in a second. This is called the decay constant. We find that the decay constant is always a small number, constant over time, and different for different materials. Here we have the decay constant for uranium-235. Both the activity rate and the number of radioactive nuclei vary over time. As a sample decays, the number of radioactive nuclei decreases. With fewer radioactive nuclei, the activity rate also decreases. From this, we get the exponential law of radioactive decay. It tells us how the number of radioactive decay in a sample decreases with time. The half-life is the time it takes for the material and activity to be reduced by half. For uranium-235, we get a half-life of 704 million years. But the decay rate we need is not uranium to thorium, but the decay rate of uranium to lead. The two uranium to thorium decays we examined earlier become a pair of complex decay chains, with some happening serially and some happening in parallel. But overall decay constants and half-lives have been measured, and the fact that there are two paths give us the opportunity to cross-check when we find rocks with both types of uranium present. We can use what we know about uranium decay to date rocks containing uranium. One significant complication arises when dealing with rocks compared to a controlled laboratory environment. In the lab, we controlled the amount of atoms in a sample. But to accurately measure the number of atoms in a sample pulled from a rock taken from the crust of the Earth can be quite difficult. But there is a straightforward way to determine the number of atoms in a sample like this. All we need to do is add a measured amount of a different element. Take a sample of the mixture and measure the ratio of the sample to the additive. This process is called isotope dilution. I've used carbon to illustrate the concept. In actual measurements, isotopes of uranium or lead not found in nature are used. The actual measurement of the ratios is done with a mass spectrometer. Like a regular spectrometer breaks light into its constituent parts, a mass spectrometer breaks a mixture of elements with different masses into separate streams for counting. The first step is to take a small liquid sample, a nanogram or so, and convert it into an ionized gas in a vacuum. This step is called thermal ionization. The sample is placed onto a filament, which is then heated to a very high temperature. This simultaneously boils the liquid and strips electrons from the sample, making them positively charged. The best filament is uranium, one of the rarest metals on Earth, because it holds on to its own electrons at high temperatures. In this schematic, the electrons are attracted to the positive plate. The remaining positively charged ions are attracted to the negative plate that has a small opening at its center. The ions then flow into a chamber containing a strong magnetic field. The ions will enter into circular curves according to their unique charge-to-mass ratios. This creates multiple streams, with each stream containing the same ions. The mass spectrometer can run for hours capturing these streams and counting the numbers and producing the ratios. And as we have seen, these ratios give us the age of the rock. In our illustration, the counts for uranium-235 and lead-207 came out at 15:1 lead over uranium. This produces an age calculation of 2.84 billion years. The counts for uranium-238 over lead-206 gave us a ratio of 55:99 lead over uranium. This produces an age calculation of 2.85 billion years. They are in agreement to within 0.35%. When they agree like this, you know you have a good measurement. This natural cross-check gives geologists an extremely accurate dating method. Uranium occurs naturally in low concentrations of a few parts per million in soil, rock, and water all over the world. Over 150 uranium-bearing minerals have been identified out of about 5,400 minerals recognized by the International Mineralogical Association. Of all of these, zircon is the most significant. A zircon mineral grain forms when it first cools from its liquid temperature to a solid, much like liquid water at its freezing point. This is called its trapping temperature because it traps elements like uranium and pushes out elements like lead. This makes it excellent for uranium dating purposes. It effectively sets the uranium-lead clock to 0. Lead atoms created by uranium decay are trapped in the crystal and build up in concentrations over time. Producing high precision ratios of uranium to lead in a zircon crystal requires multiple steps, including isotope dilution, thermal ionization, and mass spectrometry, which we have just covered. And to start with, there is a procedure called chemical abrasion to isolate the best zircon crystals in the rock. Here's how the Memorial University of Newfoundland does it. First, of course, they find old-looking rocks. The geology associated with this step is a science in its own right. 20-kilogram rock samples are typical. That's 44 pounds. Their first step is to wash and crush the rock into chip-sized pieces. They pulverize the chips into powder and pan the powder to select only the densest particles. At this point, we're now down to around a few hundred grams of material. That's just 7 ounces out of the original 44 pounds. Then they further separate the minerals by density through a heavy liquid. The densest materials will reach the bottom first. This takes advantage of zircon's extreme density over most other minerals. At this point, they have a few grams of zircon with a few other minerals. They then pass the remaining material through a magnetic field to separate out the grains with the most iron. At this point, they have a few milligrams of zircon with all other minerals removed. Using jeweler's tweezers under a microscope, they manually select the very best 40 or 50 zircon crystals. They put these under an electron microscope. This brings out the inner structure of each crystal. Some are damaged and discarded. Some are pristine and used. Each crystal is cleaned and put into a vial of hydrofluoric acid and baked for 3 days until dissolved. All the zircon molecular content is now in liquid form, including silicon, zirconium, uranium, and lead. Then they use resins and acid washes to remove all the elements except uranium and lead. We're left with a single drop of water that contains all and only uranium and lead in the original zircon crystal, usually around 10 to 100 picograms. A picogram is a trillionth of a gram. This is the chemical abrasion process. The result is called the analyte, the substance to be analyzed. They then add a carefully measured amount of lead-205 to the analyte. This is the isotope dilution step. The analyte is then placed on the rhenium thermal ionization strip, where it is rapidly converted from a drop of liquid to a gas. In the process, all the atoms have electrons stripped, making them positively charged ions. This is the thermal ionization step. The now charged ions flow into the mass spectrometer. Over hours, the mass spectrometer reports the counts and ratios for each stream. This is the mass spectrometer step. These ratios feed the equations that tell us the age of the rock they came from. This rock was 410 million years old. The oldest rocks on Earth came in 3 categories. 1, the rocks that formed here when the magma from the Great Impact solidified. 2, the rocks we brought here from the Moon. And 3, the rocks that landed here as meteorites. We'll focus on the first 2. The Jack Hills are a range of hills in Midwest, Western Australia, about 800 kilometers, that's 500 miles, north of Perth. Zircons were found in sedimentary rock, indicating that they were sourced from pre-existing rocks, which were then eroded by the weather. In January 2001, Nature published an article on Curtin University's study of these Jack Hill zircon crystals. Using uranium-lead zircon analysis, following standard operating techniques like the ones we just covered, they found the oldest solid Earth crust matter ever discovered at 4.356 billion years old. At the end of the first Apollo 14 EVA, a large soil sample was collected from the area near the lander. The bulk of the soil sample was scooped from a small crater. Sample 14163 was chosen as one of the reference soils for the Lunar Highlands suite. Scientists used a chemical abrasion, isotope dilution, thermal ionization mass spectrometry analysis on zircon crystals in the sample, like the process we used for our Earth rock sample. The oldest crystal, identified as Z59, was found to be 4.3 billion years old. This is quite close to the oldest Earth rock, indicating that they formed at the same time. We previously established via oxygen isotope ratios that they formed at the same place. These 2 findings constitute significant support for the giant impact hypothesis. But the giant impact idea remains a hypothesis. Dating methods are evolving. Different dating methods indicate different ages for moon rocks. The search for rocks on Earth continues. Another trip to the moon could change our view completely. But for now, in early 2020, the general scientific consensus is that the current version of the Earth is at least 4.3 billion years old, and the moon is close to the same age. This is interesting, but it does not tell us how long ago the earlier version of the Earth was formed. For that, we need to date rocks that formed beyond the Earth. Rocks that never went through the melt and rehardening process, like all the rocks on the Earth and the Moon. For this, we need to examine meteorites.